Hi everyone, my name is Matthew,
I'm Josh.
and our project for this semester is called Electrochemical Growth of Superconducting Rhenium. So in this research project, we attempted to design an experimental apparatus to grow rhenium films. And the reason we wanted to do this is because rhenium has applications in quantum computing. So a little background, there are type 1 and type 2 superconductors. Um, Type 1 superconductors have one state of superconductivity, and then type 2 has a higher state with a higher temperature. And for our project, rhenium is a type 1 superconductor, but when it is under strain, it transitions to a type 2 superconductor.
So our experimental apparatus here was pretty simple. We're doing electrochemical deposition, which involves oxidation reduction reactions, which take aqueous ions and essentially just deposit them onto a conductive surface that is dipped into the bowl of chemicals. So for our setup, we used 0.25 molar ammonium perrhenate, which contains a rhenium ion when it is aqueous. And that allowed us to basically reduce the rhenium down to where it deposited onto our substrate in metallic form. We also kept the entire apparatus at about 30 degrees Celsius and stirred it at 500 RPM. So we tried preparing substrates a few different ways. The first way was thermally evaporating copper onto the substrate. And the reason we wanted to do this is because it's much cheaper than the mainstream method, which is titanium and gold seed layers. Unfortunately, we couldn't get that to stick well to our silicon substrates. And when we tried growing rhenium on that, the copper just dissolved. So then we resorted to what other groups have used, which is a titanium seed layer over the silicon, followed by a layer of gold, and then you electroplate onto that gold. And we had some success doing that. We were able to grow superconducting films of rhenium. And we characterized those films first using low temperature magnetometry, which is shown in the image on the left. One of the issues with this was that we ended up getting a really broad transition, which is definitely not ideal for this kind of material. So we wanted to get a better idea of what was happening. So we went to an electrical transport measurement, and that's shown here on the right. Unfortunately, our setup for this measurement was really noisy and actually couldn't quite get down to the temperatures we needed to see the transition. On the right here, it looks like we might be reaching a transition point. However, if you look at the scale, you can see that it only really drops about 0.001 ohms, which is definitely not sufficient to conclude that it's a superconducting transition. Aside from our single layers, which we tried to characterize with measurements, we attempted to produce multi-layers of rhenium and a noble metal, which we used both gold and copper. This was something that was studied previously by a different group, and we were trying to replicate their results. Unfortunately, we couldn't get the rhenium to stick when trying to do multi-layers. It kind of grew around the sides, and we didn't get clean films doing that. So that's definitely something to try continuing in a future version of this work, is getting those multi-layers to function properly, because other groups have found that doing these multi-layers can nearly double the critical temperature, which is huge for superconductors. And then another possible idea of in the future is if you can get these multi-layers to work, try doing Crete measurements and experiment with vortex pinning and the different dynamics of superconductivity within the material.
All right, and if you guys have any questions, you can leave that in the board and we'll be happy to answer them. Bye.
Thank you.